So it is going to summarize this lecture today. Hopefully I will get to finish it, although I see within the time frame that I planned that I may not finish all of it, but I consider this lecture in chapter 6. Remember, this is introduction to what? Spectrometric methods, all right? This summarizes the lectures or the subsequent chapters that we are going to cover. Let me key us in on something that I was thinking about this morning. And this is the thing that I was thinking about this morning I reflect on my lectures, all right? Everybody has that slide. Can you see it? Updated this. You have this slide in a different form. So I updated this and say, perhaps this part is not clear, okay? So the effect of the medium on the light wave, this diagram, we have seen it before, but notice what it is saying. Better diagram, very clear. So notice what that diagram is saying, that you have light here. This is the frequency 6.0 times 10 to the minus 14 hertz per second. And the wavelength of this wave here, remember, we are just looking at light as a wave. And so you notice the lambda is 500 nanometers. What happens if it changes from one medium to another? I know one of you asked me in an exam, and this triggered my thinking. Is the speed the same? All right? One of you asked me in an exam and said, look at the front page. The speed of light in a vacuum is what? 3.0 times 10 to the 8 meters per second. When it is in air, that's in a vacuum, right? When it is in air, does that speed change? Slightly, yes, to 2.98, right? So those are two different media, right? So this is in essence what we are saying, the effect of the medium on a light wave. So notice the wavelength of the light changes from in air, from 500 nanometers to 330 if it is in a glass medium. So notice the other thing that we need to see is, does the frequency change from the diagram? Yeah. Does the frequency change? Frequency is that new. It doesn't change. But however, what changes is what? The wavelength. The wavelength changes. And that is the key that I would like to emphasize. And when it emerges from the glass medium, and then it goes to the air, you can see from 330 nanometers lambda to 500 nanometers. All right? The summary of all this diagram here is down here. So the frequency remains the same. The frequency remains the same. However, what changes is the velocity and the wavelength are going to change. Velocity and wavelength will change. Okay. Again, especially those two, the velocity will change and the wavelength will change, but the frequency remains the same. So that's one key thing that we need to note. All right? We need to note that. So that emphasis in any media, the frequency does not change. Now, let me bring up something that is important, which one of you asked again. And I think it's an important question to answer. All right, this is something that I need to answer at this point that's related to this is this. Let's go to the first one. The constant speed, remember, c, velocity is equal to, give me the formula. Velocity equals to yes, that's what I was, yes, that's what I'm looking for, all right? So notice what we talked earlier is the frequency does not change, right? And we know the speed is equal to, speed is a length over per time, right? So per time or per second, that is frequency, right? So it just means that we have that equation. There is a direct relationship between frequency and 1 over lambda. There is a direct relationship. So, oh, sorry, the constant speed means a direct inverse relationship. So inverse, direct inverse relationship between wavelength and frequency. Remember, mu is directly related to 1 over wavelength, going by the formula that we know. And therefore, if we go to the energy relationship, notice the energy relationship, which we have derived from before, E equals to h nu. Don't we know that? The energy relationship, the relationship between frequency nu of light and the energy E, we know that. You can write that equation. What's the equation again? E equals h nu. So that's the Planck's equation. E equals h nu. And so we want to, this equation, we have played with it. I'm just emphasizing this. Planck's equation, E equals h nu. And remember, there is this direct relationship, which we know. We know that relationship. We just want to substitute. So Planck constant, we know it's 6.6 times 6 to 7, so forth. To the 4th decimal point, we know, it's well known. So it's 6.6 times 10 to the minus 27 arc second, which is 6.6 times 10 to the minus 34 joule second. The same there. And so what you are looking at is in the vacuum, the velocity of light, we know the velocity. Velocity of light equals what we have said, frequency times wavelength. Frequency times wavelength, we know that, right? 1 over second, velocity, wavelength over per second. Per second is frequency. So we know that the velocity is nu, or the frequency times the wavelength. We know what that is in a vacuum, the speed or the velocity of light in a vacuum is 3 times 10 to the 10 centimeters per second, or 10 times 3 times 10 to the 8 meters per second. This gives us, now notice what we have. Going by this equation here, Planck's constant, E equals h nu. Going by Planck's constant, or Planck's equation, which we normally use, E equals h nu, and we know that velocity equals to nu times wavelength. So we know what that frequency is, just simple division there. Nu equals to c over lambda. Correct? Substitute in the equation here, E equals h nu. So this gives us E equals hc over lambda. Now let's go to the first equation. We are saying mu, or the frequency, is directly proportional to lambda. Isn't that what that is? So we know that. So which means, again, this is hc mu, 1 over lambda, is this frequency here. 1 over lambda is mu, correct? So that simply means, notice the relationship between energy and frequency. This is the equation, E equals hc mu. So notice that relationship. Is it a direct relationship or not? Between frequency and energy. It's a direct relationship. So the more the energy, whatever units that you measure the energy in, that is a direct relationship to the frequency. So if you get a frequency, are we together so far? If you get a frequency of, I'm going to give a number, 30 or 3,000 wave numbers per second, that is a unit for energy. The higher the number, the more energetic that particular bond in this case is. Does that make sense? So I would like people to know this, because usually we want that direct relationship. And if we forget about it, there is energy. You are dealing with energy. Per wave number is energy. Per wave number, that is the frequency. So there is that direct relationship. Energy equals to hc mu. And there is, therefore, energy is directly proportional to the wave number. I need to put this in red so that people know that. Okay, I need to put that in red so that people know that when you read carefully. Because these are questions you will be asked conceptually. If you forget that particular information, that energy is directly proportional to wave number, then you are missing an important information. Any questions so far as this is concerned? All right. So that is something that we have dealt with. And we have dealt with this. So I would move forward now to talk about all this we have talked about. Those are two facts that I thought while going through the lecture and say, this is important, it needs to be emphasized. Now I want to move forward to this particular slide. We've dealt with it. And now we were talking about these properties of electromagnetic radiation. Remember, we were talking about this. There are things I want to emphasize here, and that will help us summarize some of these spectroscopic methods that we encounter. So we've talked about diffraction, coherent radiation, transmission, dispersion, reflection, scattering, and polarization. I'm going to emphasize some of this. We already started talking about diffraction, all right? But I want to give another view so that every one of us gets this idea. And when you think about diffraction, you think about ripples in water, right? And they form, or you throw a pebble into still water, you see some patterns. So here is what I'm talking about here. Notice this is a wave. Light is traveling. I like this picture here as I was thinking about this lecture this morning. Now you notice there, you have here, this is a wave generator, generates a wave that has energy, or it can be whatever kind of wave, but we are talking about electromagnetic radiation. And then notice this wave is parallel. It's a parallel wave with a wavelength lambda that is shown here. It comes to a barrier here. You see X and Y. It has an aperture there, an opening. And what happens then, as we say, Mr. Brock said it very well, summarized. I remember your words. It comes to a barrier, it is bent, right? How is it bent? This is what we are talking about. That wave is parallel. Now, the portion that goes through, notice it may be straight, but it's bent as it comes out of that opening or through the aperture or a small object. You see this, if you shine light through a small aperture into a room, you're going to see this. So that's what diffraction is. Diffraction is the bending of light as it passes through an aperture or around a small object. Now, diffraction is a consequence of interference. Diffraction is a consequence of interference. Number three, when you look at this diagram here, part B rather, you're going to see if the aperture, you notice there, again, if the aperture is small, you tend to see these patterns. And these are the properties that we use in spectroscopic methods. People realized early on that this really, light as a wave, possessing this wave property, gives us information that we can use in probing molecules, probing atoms and molecules and so forth. This is not only observed, notice there, this is not only observed. You can see the lambda there. You can see lambda as this light spreads. If it is constant wavelength there, that separation gives you the wavelength. And so this is not only observed for electromagnetic radiation, but also for mechanical or acoustical waves. And you're going to observe this. So we've talked about this diffraction, how it comes about, and how that gives us information on wavelength. So diffraction of waves, did I move fast? Everybody's with me? All right. So here is another information here, diffraction of waves in a liquid. For example, diffraction increases as the aperture size. So that means that leads you to have these patterns, and those patterns give you wavelength, lambda, right? And you can see in part B here, you can see this is from Eugene Heck as here. So these are patterns, and those patterns are the ones that when you look at molecules or at the atomic level, you can actually tell the wavelength, the spacing. Okay, I think the point is made, what diffraction is and how diffraction patterns are important. Yes, sir.
So diffraction increases as aperture size decreases?
As aperture size, no, diffraction increases as the aperture size. Let's go back. Sorry. You see here. So
okay.
If it is small, that wavelength is small, right? If it's big, that spacing is big, right? Makes sense there.
Got it.
Okay. So this is another thing that, notice the first one here. This is a diffraction of waves in a liquid. You see this very often. Here's another thing that some of us may lose sight of. This is in school, actually. All this information is in school. So you want to see diffraction pattern from multiple slits. And you want to see here, there is a slit A, this parallel light, a parallel beam of light, you see it has a wavelength lambda. Here is the aperture, just one, and it creates these diffraction patterns. And the diffraction patterns would move on to the next. Notice there's it needs another slit here, B and C. So multiple slits. Now, the one in B, it creates its own diffraction pattern, correct? And the light going now through C has its own diffraction pattern. So you can see all those diffraction patterns. And those diffraction patterns, depending on the size of the apertures, they can either destroy themselves, there is constructive interference, or destructive interference. It's constructive interference or destructive interference. Now, normally, notice this line here in blue. You get dark spots and light spots. Maybe you have done a game like this. I don't know if you have done a game like this. This is a good game for mature people or even for children. You create cardboard and shine light through. And on the other side, you're going to see patterns on it, right? So you can create 2 or 3, all right? And then you can see, actually you can see these patterns very well. So this is what we are saying. From this, there is going to be some mathematical relationships that we normally are going to encounter. Now, what you'll see, diffraction patterns from multiple slits, is this kind of pattern. Okay, so that's all I would say here without wasting a lot of time here. Here, this is the math. I'm not going through that math, all right? So I don't hold you responsible for that. Are we okay there? I'm not holding you responsible for that, but if you're interested in the math, that's fine. It can be done. It's the cosines, the sines, and the relationship between the two. So it's not a very difficult math. So I want to go to, we have talked about diffraction. It encounters an aperture, it changes course, and therefore you're going to see some information about the wavelength. And now let me talk about coherency, a coherent radiation. Because in your homework, there is something defined these times, right? And this is one of them. Coherent radiation. Coherency occurs when 2 waves have an initial phase difference of 0, something coherent. Just using normal language, coherent. You see a matching band, right? And they are matching. That's coherency. Is that the case? So coherency occurs when 2 waves have an initial phase difference of 0 or constant for a long time. If the initial phase difference is 0, they are matching in phase. And so they are coherent. So we use that property. Or for example, you can separate them by a given factor so that they can match in for some time. So the conditions for coherency of 2 sources of radiation, for 2 sources of radiation to be coherent are this. You must have identical frequencies. For coherency to occur, you must have identical frequencies. And The phase relationships remains constant with time. The phase relationships, the phase relationships between the two waves or the two sources of radiation must remain the same. Okay, identical frequencies. You have two sources of radiation with identical frequencies, they will be coherent. You know, out of this, let me tell you what we are thinking about here. You may not know the bigger picture. The late Professor Zewaili, you know Professor Zewaili of UC Berkeley, he passed some years ago. He had done his PhD, he had done his postdoc, and went to look for a job. Then he thought about this coherency and how to image molecules when reactions occur, all right? And you know what we have currently is what we call femtochemistry. It's a branch of chemistry, I mean, how to image reactions. Put cameras at various spots, shoot lights through lasers, and then you see if it's a reaction, you can actually image it at the femtosecond level. So that's why it's called femtochemistry. You can do this for molecules like DNA and so forth. It's a lot of fascinating physics. He won the Nobel Prize for these kinds of things. So when people use these ideas, and then you probe into molecules, you come up with information that is useful in reaction kinetic studies, studying of molecules, and so on. So in coherency, how do you test for incoherency? You illuminate the slits with a W lamp. What is W? What's W? Need an answer. Look at the periodic table. That's tungsten, right? So you illuminate the slits with a tungsten lamp, and that's a test for incoherency. So, and what are the results? The results, the disappearance of the dark and light patterns. Remember, there's the dark and light patterns that we, can I move back so as to emphasize this a minute? You see here, we talked about this. Notice that you have the dark spots. You have the dark spots and the light spots, all right? So you have this kind of patterns from multiple slits. Now, if you want to test for incoherency, you just illuminate the slits with the tungsten lamp, and the result will be the disappearance of the dark and light patterns. That means they're incoherent. And the reason is the more or less uniform illumination of the screen will be there. And this is important. That's how you test for incoherency. Okay, so I've emphasized these important facts. Do you have any other questions here, either from those of you who are here and those of you who are logged on live stream? Any question? All right. Now then, I will emphasize this Raman scattering when I want to cover the summary of interaction of light with matter. This is what we are dealing with on scattering. And I want to note something here before I bring this up, all right? That the intensity of the scatter, notice there is light. The light interacts with matter. In this case, matter is what we are analyzing, the analyte, atoms, molecules, all right? So the scattered light, so we are saying a small fraction of radiation is transmitted in all angles from the original path. So this, notice this, what is represented here, very simplistically here, to give us the idea. So you have the light here, radiation of light, interacting with matter, interacting with the chemical species, and the light is going to be scattered. And you can collect the scattered light. You can collect the scattered light. The scattered light gives you information about the vibrations of those atoms or the bonds specifically. And that's what we are saying. The intensity of the scattered light is directly proportional to 1 over lambda to the 4th. It's a very weak phenomenon. Lambda is the wavelength, so it falls off very quickly. Can you see that? That the intensity of the scattered light is proportional to 1 over 4 of the wavelength to the 4th power. This is Raman spectroscopy. We are talking about the use of Raman spectroscopy here, all right? So I'll come back to this. So now, there are 4 things that we need to know about this scattered light. The scattering of this radiation, right? Scattering of this radiation gives us some terms. Most of this, when I talk about scattered light, normally it talks about Raman scattering. Raman scattering. Are there people called Raman? People are called Raman. Where is their origin? R-A-M-A-N. Raman. It's in India. Yes, southern India. We call it Raman scattering because the first person, 1928, who won the Nobel Prize is called C.V. Raman, I think. Okay, so he got that phenomenon and documented it. Are we together here? So he documented it and then gave us data, so it bears his name. Are we together here? It bears his name. He won the Nobel Prize around 1932, I think. 28, he wrote the papers, 32, won the Nobel Prize. So all I'm saying here is this weak phenomenon, they did spectacular experiments then. And when was this? 1928, right? We did not have very good instruments, right? I have an instrument in the lab, in the ICPMS, the Raman spectrometer. Anyone who has been in that room doing some meta-analysis? There's an instrument here, and it has lasers in it. And it's because of it's a weak phenomenon. Now, please notice what I'm trying to emphasize. The intensity of the scattered light is proportional to 1 over lambda to the 4th, which tells us that that intensity falls off very quickly. So how can you enhance that intensity? That's where we need lasers. Are we together there? We need lasers. So up to 1986, we did not have good lasers. And then from there, lasers came into being. They have not been with us for long. I don't know if you know. 1986, it recent. And so that's when lasers became popular. And then Raman spectroscopy became very, very useful. We use it in all kinds of analysis. All right. So terms associated with scattering of radiation are, so The molecules or the aggregates of molecules with dimension, we are talking about the types of scattering. There are three types of scattering. You have Rayleigh scattering, you have anti-Stokes scattering, and Stokes, all right? So let's talk about Rayleigh scattering. We're together there. Rayleigh scattering usually occurs when molecules or aggregates of molecules with dimensions significantly smaller than the lambda of radiation. It's smaller than the lambda of radiation. The intensity is proportional, we've said, to the inverse fourth power of the wavelength. I is proportional to 1 over lambda to the fourth. And this is what you see. This is why the sky is blue. It's because of Rayleigh scattering. Rayleigh is what we see it as blue sky because of light being scattered. And we are saying that occurs because of the molecules that scatter the light. Usually they are significantly smaller than the lambda of radiation. So that's Rayleigh scattering. Here is the next one. We talk about scattering by big molecules, the Tyndall effect. We see this, for example, if you shine light in milk. Milk has particles, it scatters light, right? So we have the Tyndall effect, the scattering of light by big molecules. So this occurs for colloidal dimensions particles. The scattering can be seen by the naked eye. And it's used for measuring particle size and shapes of polymer molecules. Polymer molecules are big, so they can scatter the light. You can measure their sizes. Now, then the next one, notice the kinds of scattering that we are talking about. We have Rayleigh scattering, we have Tyndall effect, and we have the Raman scattering. The Raman scattering involves quantized frequency changes. Quantized frequency changes. The keyword is quantized frequency changes. And the changes are the results. These changes is one keyword. In all these words is one keyword there. Can you see the keyword? I want you to look for the keyword there. Raman scattering, read the sentence. I want you to pick the keyword, pick out the keyword. Polarization. Polarization. So when you hear of Raman scattering, the word that comes to mind is polarization. And so it is a quantized frequency changes. It's quantized, that's all right. These changes are the results of vibrational energy transitions that occur in the molecule as a consequence of polarization, a polarization process. You shift the electrons around the molecules. That's what the scattering of the light involves. So it's a polarizability. When you hear of infrared, the key word is changes in what? I think we talked about it. A change in a dipole moment, right? I used carbon dioxide, do you remember? I used carbon dioxide, stretch as the simple, or two molecules, carbon and oxygen. That is a dipole moment. For CO2, if you have two oxygen atoms at the end, if they move with the same dipole, they cancel each other. You cannot see infrared, but if they are imbalanced, then you can see an infrared. That is a dipole moment. In the Raman scattering, for you to see Raman scattering, which results in vibrational energy, the two types of spectroscopies usually complement each other. For you to see Raman scattered light, then the molecule has to be polarized. We call it polarizability. All right, so we've dealt with those, and now I want now to start here on these major classes of spectroscopic methods. In my plan this morning, I said maybe I would cover this. And when I thought about it, I said, I wish I had 2 hours in class. All right. So this lecture and the Monday lecture will be concentrated on this before I start chapter 7. Am I clear here? So let me go through this and then start picking out each of these spectroscopic methods one by one. And then from after chapter 7, then we start talking about each one of these methods that we use in analysis. All right, the class of spectrometric methods, we have emission. Light is emitted. Now there is P. What is P again? P is power. Radiant power. Remember in the diagram on A equals minus log T, we encountered that. Remember, minus A equals minus log T, there is a relationship between P naught and P transmitted light. There is a relationship between those two. There's a relationship between the transmission. How did we define transmitted light? T is equal to in terms of power, radiant power and emitted power. In terms of power in and power out, energy that is absorbed absorbed by the molecule. So it's going to be P over P naught, right? So in this case, this is what we are saying. Notice you have the radiant power that is measured is the emitted E, P sub T or PE sometimes. So the emission, the emitted amount of light, we talk about emission, then this is directly proportional to concentration. So the emitted amount of light, this is Beer's law. In the Beer's law, or if we are talking about emission, specifically, it is atomic emission. So the emitted power, the emitted radiant power is proportional to the concentration. That means we can use, so we are saying here that power is proportional to concentration. And if that is the case, then the proportionality constant is K. So we have this proportionality constant. So the emitted power is equal to K times C. That's for emission. It has atomic emission. When we analyze atoms like potassium, group 1A molecules that easily emit the electrons. Then we have luminescence. And again, you will see in all this, you want to see P equals Kc, P L, P sub L. You can see that P sub L is directly proportional to concentration. There is that proportionality constant. And scattered light, the power of the scattered light is equal to K times C. So you can see that is Beer's law, Beer-Lambert law. But you are going to see in luminescent light, luminescence, we talk about the atomic and molecular fluorescence and chemiluminescence. So we talk about fluorescence, it is because molecules luminesce. Then we have Raman spectroscopy and tapedometry. You measure that scattered light within the oceans and the skies. So that is scattering of light. Then the last one here, I want to emphasize this again. the absorption, the incident power, and the transmitted power is compared. The incident power P naught and the transmitted power P. You compare the two, and you can see A equals minus log. Remember the formula we gave? A equals to minus log T. And this is what we have encountered. And T is really P over P naught. T is P over P naught. This is T here, log T. And we know absorbance is epsilon BC. All right? And so we use this in atomic and molecular absorption. This is what we use, absorption. So as I've said, in the next class on Monday, I want to pick out on each of these. And initially, in the notes, I've given a diagram that summarizes this, but I've now broken it down so that we can go through each one of them and summarize it with the diagram that I intended to go through. Does that make sense? So that's what we're going to do, and Monday is important because of this. Once I summarize that diagram, what we call the Jablonski diagram, then it's going to come again. So make sure on Monday you don't miss that lecture. All right. I think I'm going to stop here unless any one of us has a question. That's their question for me. Okay, I'll meet you at 11 o'clock today in the lab. Those of you who are doing UV and so forth, we'll meet in the lab, and then we'll do the experiments. UV this, infrared, and HPLC.